Experiment 12, determination of solution pH. I, as always, have my goggles and gloves and a lab coat on for safety, and am following the procedure detailed in the lab manual. So we're doing another serial dilution, just like we did in the spectrophotometry lab, where we diluted that blue copper sulfate solution. This week we are diluting various acid and base solutions to get different concentrations of those. So again, in the pre-lab material, we went over what a dilution equation is, that molarity times volume equals molarity times volume, because number of moles is constant. So we'll follow along our steps in order. We're going to take 100 milliliters of 1 molar acid solution. So here I have, supposedly, as long as it hasn't evaporated, 1 molar exactly hydrochloric acid solution. And since it is 1.0 moles per liter and it is a strong acid, that means that every single 1 mole per liter of HCl hydrogen chloride molecules were added to this. They 100% broke apart into H plus and Cl minus. So this is 1 molar H plus and 1 molar Cl minus, although the Cl minus we don't really care about. And since pH is the negative log of the H plus concentration, that would be a pH of 0. And so I'm going to get a 250 milliliter beaker that I have just cleaned. And I'm going to dry it off, if for no other reason than just for visibility purposes. And I'm going to put about 100 milliliters of the acidic solution into the 200 milliliter beaker. Now beakers, just like flasks, are not precision measuring devices. This one says right on it, plus or minus 5%. And so I have around 100 milliliters, but that's all I need, is around 100 milliliters. Okay, I'm going to take 90 milliliters using a graduated cylinder, because I want to get a little bit more precision in this one. 90 milliliters of water, using a 100 milliliter graduated cylinder to another 250 milliliter beaker. So, get my graduated cylinder, get the 90 line down to eye level, and do I need to use a pipette? Let's see if I can get it exact. Done. 90 milliliters of water. Second 250 milliliter beaker. Labeling this beaker 1. And I'll put the 90 milliliters of water in here. Get my 10 milliliter graduated cylinder, which is clean and dry from the last experiment. Cleaned, not so dried. Get that sucker a little bit drier. Going for relatively good precision here. And I want 10 milliliters of the 0 solution. Eye level. And needs to be mixed. Just because I know I'm going to be using it next, I'm going to stir it with the pipette as well. Alright, so that's pH 1. Then I'm going to get a third 250 milliliter beaker. That's pH 1. I'm not going to just take 10 milliliters and 90 milliliters, approximately, to dilute it by a factor of 10, which was diluting it from 0 to 1. I want to dilute it this time by a factor of 100. I don't want to end up with a whole bunch of beakers here. Like 14 beakers is a pain in the neck. So we got it down to 9. All right. So I have that guy there, third 250 milliliter beaker. I'm going to label this one 3. And I'm going to take 1 milliliter of the solution in beaker 1 and 99 milliliters of deionized water. So the way I'm going to do that is 99 milliliters of water. This I got to do really carefully. Might need a pipette for this one. I had exactly 100. I need exactly 99. Exactly 99. And exactly 1 milliliter of number 3. Number 1 to make number 3. 20 drops is considered a milliliter, but I want to use my precision measuring device here to get it really exactly, rather than just guessing. I'm going to leave this pipette in pipette number 1, and I'm going to pour the 100 milliliter solution. These things contain rather than deliver, but we're discounting that as well. And stir. Just have my deionized water in it, so I'm going to use it to make number 3 really well. Mix really well. Next, a 10 times dilution again, so 90 milliliters of this one, of water, rather. Again, making the solutions in this lab takes longer than actually doing the lab. $90 milliliters of water. This is going to be a 4. Another beaker. Is in. Okay, I want to rinse my 10 milliliter graduated cylinder with a little deionized water, just in case it's got any residual from the last one, which would be much more concentrated. And I'm going to take 10, nope, we already had a 1 and 3. Pipette in 3. I'm going to take 10 milliliters of 3, 90 milliliters of water. Again, we're ignoring the fact that solutions can expand or contract upon mixing. Close enough for this lab. We'll see how exact I make my solutions up when we measure their pH. 10 milliliters of 3, 90 milliliters of water into 4, and this was my deionized water pipette. Stir well. All right, so that's a 4. Step 5. About 100 milliliters of our base solution. I have 1 molar sodium hydroxide here. I'm going to put about 100 milliliters of that into yet another 250 milliliter beaker. Since it is a strong base, it is 1 mole Na plus and 1 mole Na plus and 1 mole per liter OH minus. Strong electrolyte, going back to the light bulb experiment. And so, it fully ionizes in solution. We would have a pOH of 0, which means that the pH is 14. But we don't really go over converting pOH into pH in the 127 lab or the 127 lecture. But this is pH 14. I'm not going to have enough room down here to widen out my angle later. I'll put it over here, right on the edge of the frame. We can sort of see it. Maybe I'll shuffle some things around here. pH 0, 1, 3, 4, and 14. Cool. All right, we're doing the same kind of serial dilution from the base this time, making lower pHs. So we'll add 90 milliliters of the water again. I have to refill my water here before too long. 90 milliliters of water. Beautiful. Take a touch out of there. Good. And 10 milliliters of the 14. I'll just pour, at least at the beginning. Perfect. Into our next beaker, which is labeled 13. Give this a rinse. And need a refill. Give our graduated cylinder a rinse with some deionized water. Because this is the one where we're doing a 1 to 99 dilution. Air bubbles. Eye level. Down to 99. Let's get our 1 milliliter of 13. 1 milliliter of 13. Make sure it's stirred really well. I'm sure it was. In the graduated cylinder, pouring it in, but we'll just make sure. 1 milliliter of 13. Like how I caught myself there. Into here. Can stay where it is. New beaker labeled 11. Counter. In you go. One more rinse. Deionized water. $90 milliliters of water. Air bubbles. Yeah, look at that. The air bubbles was perfect. One more beaker. Now, as we're spending all this time making these solutions, carbon dioxide from the air, even though there's only 1% or so of it in the air, is dissolving into each of these solutions. When CO2 combines with H2O, you can get carbonic acid, H2CO3. Carbonic acid, of course, is an acid and can change our solution concentration in pH. 90 milliliters of water. $10 milliliters of number 11. In we go. And we will label this guy 10. Swirl, 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 swirl. Last but not least, a beaker in the middle, which we'll have to leave unlabeled because my 7 seems to have disappeared. pH 7, theoretically, deionized water. All right, after all that, our preparation for the lab is complete, and we can start measuring the pH of these various solutions. So how are we going to do that? Well, we can do it a variety of different ways. We will use first a pH meter, which I have here. Okay, just on a ring stand, hold it upright. It uses our old pal, the LabQuest, and it's soaking in a buffered solution that should be around pH 4 or pH 7 or pH 10. This one appears to be near pH 4. But we will have a waste beaker nearby, so that we can measure, rinse off this pH probe. Now the pH probe is very delicate, and we got to protect it by handling it carefully. It always has to be soaking in a solution, and so, for brief amounts of time it can be outside. But we're going to rinse it off with our deionized water in between every measurement. Okay? So, let's measure our various solutions, 0 to 14, and see the pH value that we get in each one. So, here we go. Data sheets at the ready. We will measure the pH first. Let's start in the middle. Let's start with pH 7 and see if our water that we used to make all of our solutions is in fact pH 7, or if our meter has not been calibrated properly, or what exactly is going on. Okay? So, interestingly, our pH 7 water appears to be pH 4.25 according to the pH meter. Either the meter is wrong, or the water is rather acidic, which is entirely possible, I suppose, but that's pretty low. Let's see what happens as we go to the acidic direction. minute of rinse, especially the tip, which is where the actual reading is, the actual probe is. All right, so 4.25 for our pH 7 theoretically solution. Let's see what we get at pH 4 that we were thinking was pH 4. Oddly higher. 4.85. This is why you always need to calibrate your instruments and maybe use more than one instrument, which is what this lab is. We're going to measure the pH of these things multiple ways and see what we get. This lab doesn't work particularly well, which is a nice lesson and why I'm considering leaving it in the manual. And then also it doesn't work very well, which is why I'm considering taking it out of the manual and measuring pH of things around your house, like oven cleaner and window cleaner and things like that. All right, so pH 4 ended up being significantly higher. 73. 5.73, and we were expecting a pH 4. Let's see if we at least can get lower when we go into pH 3. We know there's more acid in it, because you watched me dilute it. So far, so good. It at least is lower. The water out of the tap, out of the deionizer, when I refilled the bottle, the deionizer hadn't been used in a while, and it seems like that last water that I added there may have, out of the deionizer may not have done such a good job of deionizing. And so our pH 7 water was freshly not deionized, and it seems to have been a problem. But we'll check other ways to find out. 3.17, let's say. 3.17, we were expecting 3, so that's our first one that's close. Remember, every 1 unit pH change is a change 10 times concentration. Just like sound pressure level, decibels, is a 10 times change for every 1 unit. All right, we're expecting pH 1 here, based on our concentration and our dilution. Unlike the spectrophotometer last week, the pH meter takes a little while to equilibrate. I'm also jiggling it around because you can't have any air bubbles underneath the probe or it messes things up. So we're expecting 1, and it looks like we're at 1.63. Again, we were expecting 1, and we're at 1.63. Let's see if 0 truly is 0. We might be hitting the limit of our meter as well. That's another issue. Electronics have limits, have measuring limits. And when you get to the extremes of the limits, another reason that Beer's law in that spectrophotometry lab only is valid technically between 0.2 and 0.8 is below 0.2 you start to hit the limit of the instrument. pH 0, we're thinking. This is our original 1 molar acid solution. I do not know how long it's been in the stockroom, but it looks pretty fresh. It's not pH 0. It has seemingly neutralized a bit, but again, we'll measure it different ways. Oh, we're getting down there. Let's leave it for another few seconds and see what we get. 0.83. We were expecting pH 0. Not so bad. Definitely low pH. We may not be able to trust this to the 100th place, maybe not even to the 10th place, but we can definitely determine if is it an acid or a base. Let's go to the base side of things and see what we get. And the rinse that I'm doing here of deionized water, based on our test of the water, not so deionized. All right, we're expecting pH 10. Based on our dilution, it looks like our deionized water being so acidic may have horked things up when we diluted so extensively on our base side. And this is why you got to measure stuff and test things. Get this really strange result in your lab, and you don't bother to think about what could go wrong, and you end up publishing a paper, and everybody thinks that you're crazy. Or even worse, they believe you. Vaccines are bad. Ugh. Global warming isn't happening. Ugh. Yeah, that is called non-science. Sounds a whole lot like nonsense for a reason. Okay? Our deionized water that we used to dilute our base was incredibly acidic based on our test. And so instead of pH 10, we have a pH of 3.48. We will confirm it with some other pH measuring instruments. But there we go. Why didn't I just delete this and redo it in the video? Because I think that this is a valuable learning experience. I'm not panicking, oh my God, I got it wrong. No, I'm moving on and explaining my error. Let's check 11. See where the base ends up overwhelming our not deionized water. Still not yet. It is more basic than the 10, which is what we would expect since we made 10 from the 11 by diluting it with very acidic water that should have been deionized. But we're still only in pH 5 range. We're expecting a pH of 11, and we're expecting a pH 5. Now, what this is going to screw up later is when we use our universal indicator, we're going to get not as pretty a rainbow of colors as I would have liked. But so be it. 5, no, we're up to 6. 6.27. We're expecting 11. Expecting 11 based on our dilution, but we diluted with not deionized water. So we're at 6.38, let's call it. 6.38. At some point, we're going to have so much base, maybe at 13 and 14, that it's going to overwhelm the deionized water. But we'll see. Expecting a 13. Looky there. That not deionized water had some acid in it, but not enough to counteract the extreme basicity here. What's interesting is that it's above 13. You watched me. I measured it really carefully. 90 milliliters of water, 10 milliliters of pH 14 base. But let's check the 14 and see where it is. Again, the meter might be miscalibrated, and our water certainly seems to be off. 1331, let's say. 1333. How about? Yeah, 1333. We're expecting 13. Expecting a 13. We got a 1333. Final rinse. Final test with the meter. Expecting 14. It was 1 molar base. It's definitely higher than 1333 right off the bat. Will it get to 14? It's kind of the limit of the meter. We're at the edges. Maybe not. $13.76. A fine vintage. $13.76 seems to be all we're going to get out of this expected pH 14. Right? Just for fun, one last test before I put away the meter. Let's go back to our deionized water and see how we fare now, having gone to that other end of the spectrum. We're going to have to let this settle for a little while. Dropping down from where we were at 14. Again, this is not immediate like the spectrophotometry. We're dropping through 7 now. Let's see, maybe we'll hold. Maybe our water is deionized. Always good to repeat your experiment, if not 3 times, at least twice. No, we're dropping into the 6s. So I think we'll stick with our original reading that our water is seemingly very acidic. Just see if I have a note on that from in the past. But I don't think that I do. No. Just notes that this lab doesn't work very well. We're definitely going to hit into the 4s, so we'll stick with our original value that we had before. All right, to recap it, I just put it back in the buffer bottle and tighten the cap, and I'm done with the pH meter. And we'll move on to measuring the pH of these 9 beakers via the litmus paper and the universal pH strip paper and the Yamada's universal indicator. We're going to go old school and use litmus paper. This is blue litmus paper, and this is, as you can probably tell from inside it, because the label is all messed up, red litmus paper. Now, both of these types of papers have something called litmus that it's been dipped in. Litmus is an interesting plant-animal combo. It's a lichen that is a natural pH indicator. There are others out there. Chrysanthemums, the flowers, will grow red flowers if it's in acidic soil and blue flowers if it's in basic soil. Just like litmus changes color red in acid and blue in base. And there are other examples in nature. Similarly, the Yamada's universal indicator that we'll use later can be made at home with cabbage juice. If you get red cabbage and chop it up and soak it in some water, you end up with a pH indicator. And so if you added that cabbage juice to vinegar, it would turn red, and if you added it to oven cleaner, it would turn blue. So we use the 2 different colors because if you dip red litmus paper into acid, it's not going to do anything because it's already red. But if you dip blue litmus paper in acid, then it will turn red. All right, so let's try that. We'll start with the red litmus paper column first for all of our expected, based on our dilution, solutions. So I've got the 0 here, and I'm going to add the red litmus paper to it, and no change, as expected. It just stays red. Get a bunch of these papers out because I need 9 of them. pH 1 expected. Red litmus paper. I could just use the other end from the first one, but I'm not going to. No change, as expected. So far, so good. You know what? I will. I'll be environmentally conscious. Using the end that I haven't used before. I'm going to go for the 3. Dipping it in. I could use a dropper to get a drop onto the paper, but this is just for speed. 3. No change, as expected for the red litmus paper, because we are expecting acid there. 4. No change, as expected. Now, exactly neutral shouldn't change, and it doesn't. Okay? No change. Now, here's where we are expecting a change. We should see for pH 10, that's our next one, pH 10, our next one, we should see red litmus paper turn blue. But it doesn't. This seems to be confirming our pH meter that we don't have pH 10. We expected pH 10 based on our dilution, but our water that we were diluting with seems to have been contaminated. Expecting pH 11 should turn blue. No change. No change. All right, 13 now on the meter was acidic. Was basic. unlike 10 and 11, which were acidic, even though we didn't think that they should be. So pH 13, red litmus paper, blue, definite change. Now all litmus will tell you is acid or base. Doesn't tell us the exact pH. Let's go for 14, which we know is more basic. Also blue. Now, if I look at the two ends of the paper that I used, this is 14 at this end, 13 at this end. There's no visible difference. Okay? That's not what litmus paper is capable of giving us a difference. It's basic. We know that. 10 and 11, we're expecting basic. According to the pH paper, it's acidic. According to the pH meter, also acidic. Our dilutions appear to have been contaminated. Let's, because we can, confirm yet again with the blue litmus paper. Got a bunch of that here. We'll go in the same order. I have blue litmus paper. If I dip it in base, it shouldn't change. If I dip it in acid, it should change. Expected 0. Definitely turned red, as expected. Let's use the other end. Expected pH 1, we are expecting a change. Absolutely. Changes to red. So, 0 and 1 are acidic as expected. 3, expected. This litmus paper might be old. Give it a minute. I don't know if the camera is going to pick it up. There is a bit of red at the edges. Try the other end. No, this one is acidic. There, this end is a little bit better. Definite red on the end, if the camera will pick it up. But certainly not as dramatic as for 1. You know what? Just because, try a different piece of paper. Try a different bottle. Might be an old bottle. Same effect. I'm going to switch bottles. Litmus paper. I have a different blue. Of course not. All right. Let's see what happens when we do 4. Inconclusive. It's mildly, slightly, possibly a little bit turning red, but hard to say. But based on our other test, the red didn't change and the blue didn't change either. Litmus is not that useful here. It seems like it might have turned red a little bit. Based on our pH meter, it's definitely acidic. With the litmus paper might be old and hard to tell. We tested our neutral, supposedly pH 7 before and didn't get a change with the red litmus paper. We're also not getting much of a change with the blue. 10, interestingly, seems to have changed more than the 7 did. See a little bit of red there, but not dramatic. This would not raise warning signs to me that, hey, you've got an acid when you're expecting pH 10. This is looking like it's just staying blue, maybe turning a little bit pink. It's hard to say. So, not the most useful test. Let's see. We'll go on and do 11, 13, 14. 11. Proper procedure again is to dip a stirring rod in there and touch it to the paper. Just not doing that for time. No change. As expected, but doesn't necessarily agree with our meter. 13, no change, definitely as expected. Switch it around to the other end. Final test for 14, and also no change, not even a hint of pink on there. So, litmus paper, limited utility. What can be more useful is a paper that is universal. You can measure pH 0, should be red on this paper, all the way down to really, really dark blue at pH 14 with this paper. So this is a universal indicator like the Yamada indicator, but dried onto a piece of paper. So this is going to be our pH strip. Measurement. These are kind of dipped in wax, so you have to kind of peel one off. Some of them, the universal indicators, have 4 color strips on there, and you can measure that. You have to look at all 4 colors, which gives you a little bit more of a precise reading. So here we go. We'll rip off a strip each time and match it to the bottle to see what we see. Rip off a whole strip so it's easy to hang on to. Expecting pH 0. Well, it's definitely red. The question is, if we hold it up next to the bottle, is it a 0 or a 1? To me, it looks like a 0. So the universal strip for the 0 does seem to tell us that it's a 0. Okay. Let's try our expected pH 1. Definitely not red, definitely more orange. To me, it looks like it's somewhere in between 2 and 3. You can decide for yourself, but I'd call that a 2.5. 2.5. All right. Expecting a 1. Got a 2.5. Let's try 3. Expecting a 3. To me, it's a 5. It's definitely not a 3. To me, it's a pretty much exact match for a 5. Even though we were expecting a 3. Let's try 4. Let's see what we get. So we're all over the place comparing the meter, litmus, so on. So be it. That's why we check things different ways. Expecting a 4. Pretty clearly a 6 on here. Expecting a 4. The universal strip pH says a 6. It's this greenish color. I wonder what 7's going to say. Again, the meter might have been miscalibrated. Oops. Helps if you don't drop it into the 4. We can leave that there. Not going to change the solution. 7. Expecting a green for a 7. It's not. It looks pretty much the same as the last one did, a 5. This pea green, expecting a 7, it's a 5. The meter said it was even more acidic than that. It's definitely not 7 though. The litmus paper didn't change, either one, so that kind of indicates a 7, or not acidic, but we know it's acidic. So, all right, expecting a 10. Nope. If anything, it's even lower than a 6. I think that the 10 is a 5, based on this universal indicator. Well, we knew it was acidic based on the meter, and the litmus paper was unchanged and inconclusive, but this universal strip, pH strip, seems to say that it's pH 5, lower than our deionized water, which is weird. On to 11. Still acidic according to the meter. Still like a 6, right? We're not all the way to 7, I don't think. No, right? It's still lighter green than 7. from around a 6, between a 6 and a 7. How about that? It's between a 6 and a 7. 6.5, let's say. So we're expecting 11, and we're seeing a 6.5 based on this pH strip color. It's not quite pea green, but not quite forest green. Somewhere in the middle there. 13 should definitely be acidic. Definitely basic, according to everything we've seen so far. And look at that. Yeah, I'd say it's a 13. Right? Not quite a 12. I'd say it's a 13. So our pH strip seems to confirm that we were expecting a 13. 14 is hard to tell any difference between 13. It's just even darker. Let's find out. I'd go for that. 14. Right? Is it darker than 13? I think so. 13 versus 14. There we go. All right, so that's the universal indicator strip, or pH. It says strip pH on the data sheet. Doesn't mean take your clothes off and measure the pH. It means a universal indicator dried onto a piece of paper, a strip of paper. For the last one, let's make it a little pretty. I'll take a pipette, new one, and we'll make a rainbow, because Yamada's indicator and cabbage juice indicator are kind of like what's dried onto that paper indicator, in that it reads universally from one end of the spectrum to the other. So I only need a couple of drops per beaker of this, looks greenish, solution as it comes out of the bottle. 1, 2, 3, it's really light if I do that. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So let's call it a milliliter that I'm going to add to each one. Is going to be the only one that's out of order, I think, based on our previous experience. Number 10 we made from the base. 0 to 4 we made from the acid, and then the neutral was just the water by itself. So this 10 is a screw up because we started from the base and went down, but with very acidic water. Give each one a swirl. And I think you'll see colors that are very similar to what we were looking at on the strip. That for pH 0, we have this sort of light peach color. 1 is a little darker peach. 3, sort of similar to 0, peach color. 4, we're getting a little greener. 7 is not really 7, we're back to this peach. 10 is not really 10, back to the peach. 11, there we go. Now we have a base color, sort of a greenish blue. 13, deep purple, nice band. And 14, a dark navy blue. So what are you getting out of this lab? What can you conclude from this lab? Well, I think that this is a nice example of how data can vary depending on your instrument. It can be subjective based on how you name each color. You don't have to name them what I named them. You might call this tangerine instead of peach. I don't care. And how you might need to use multiple instruments to confirm your results and maybe repeat the experiment. I mean, what we really arguably could and maybe should have done is gone back and fixed this guy. Right? This is definitely not pH 10. No test that we did said that this was pH 10. Why? Because our pH 7 is not pH 7 either. We used contaminated water for our experiment. That's not good. You should repeat the experiment if you wanted to get precise results. However, I think this is a valuable example in being able to explain anomalous results. And with that, I leave you to discuss the lab further, perhaps with your instructor.